frustrating wait for your computer to boot, the endless loading screens, the spinning wheel of death. For decades, this was the unavoidable reality of digital life. The bottleneck wasn't your processor or RAM. It was the slow, mechanical hard drive, a relic holding back an entire industry. Today, that frustration is largely a memory, thanks to a quiet revolution, the solid-state drive, or SSD, which didn't just speed up computers, but fundamentally reshaped what was possible. For nearly half a century, traditional hard disk drives, or HDDs, were the undisputed kings of mass storage. These devices relied on spinning platters coated with magnetic material, where data was written and read by tiny electromagnetic heads hovering just nanometers above the surface. Imagine a record player, but infinitely more precise and delicate. While remarkably innovative for their time, this mechanical design introduced fundamental limitations. Accessing data meant waiting for platters to spin up to thousands of revolutions per minute, and for read-write heads to physically move across the disk. This physical movement introduced latency, a delay that became the primary choke point in computing performance. Even the fastest processors and most abundant RAM couldn't overcome the physical speed limit of a spinning disk. Every time you opened an application, loaded a game, or simply booted your operating system, you were waiting on mechanical components to retrieve scattered bits of information. The sound of a whirring hard drive was the sound of your computer struggling to keep up. At its heart, an SSD is a storage device built entirely from non-volatile flash memory, similar to the USB stick you might carry in your pocket, but vastly more complex and powerful. Unlike HDDs, SSDs have no moving parts. Instead, data is stored on interconnected flash memory chips, typically NAND-based. This is where the solid-state in solid-state drive comes from. It's a purely electronic device. Without mechanical components, SSDs can access data almost instantaneously. When your computer asks for a piece of data, an SSD doesn't need to spin a platter or move a head. It can simply locate the data electronically and deliver it, often in microseconds. This fundamental architectural shift allowed SSDs to bypass the physical limitations of HDDs, unlocking unprecedented levels of speed and responsiveness. The most immediately noticeable impact of SSDs was, without question, raw speed. Think about booting your computer. With a traditional HDD, that could take minutes, sometimes 5 minutes or more, filled with disk activity noises and a sluggish desktop appearing piece by piece. Switch to an SSD, and suddenly your system is ready in mere seconds, often under 15 or even 10 seconds. This wasn't just a minor improvement, it was a paradigm shift. Applications that once took half a minute to load, like Photoshop or a demanding video game, now sprang open almost instantly. Large file transfers, which previously might have tied up your computer for hours, completed in a fraction of the time. This burst of speed made computing feel genuinely modern, fluid, and far more productive. The entire user experience transformed, making sluggish machines a thing of the past. Beyond sheer speed, SSDs brought a host of other transformative benefits to the computing landscape. Consider durability. Without moving parts, SSDs are far more resistant to physical shock and vibration. Dropping a laptop with an HDD could mean catastrophic data loss. With an SSD, the risk is dramatically reduced, making portable devices truly robust. Then there's power efficiency. HDDs require energy to spin platters and move heads, generating heat and draining battery life. SSDs consume significantly less power, extending the battery life of laptops and reducing energy costs in data centers. And, of course, silence. The constant whirring and clicking of an HDD, especially under heavy load, became a familiar background noise for many. SSDs operate in complete silence, contributing to a much quieter and more pleasant computing environment. Finally, their compact size opened up entirely new possibilities for device design. Traditional 2.5-inch and 3.5-inch HDDs dictated certain form factors for laptops and desktops. The emergence of smaller M.2 SSDs, which look like a stick of gum, allowed for the creation of incredibly thin, lightweight ultrabooks and more compact desktop builds, completely changing the aesthetics and portability of modern computers. Despite their clear advantages, SSDs didn't instantly dominate the market. Early SSDs, first appearing in the commercial space in the mid-1990s and then trickling into consumer products in the mid-2000s, were prohibitively expensive and offered very limited storage capacities. A small 64 GB SSD could cost hundreds of dollars, making it a luxury item only for enthusiasts or specialized enterprise applications where speed was paramount regardless of cost. For years, the common advice was to use a small SSD for your operating system and essential programs, and a larger, cheaper HDD for bulk storage. However, as manufacturing processes matured and demand grew, prices steadily fell. Advancements in NAND flash technology allowed for greater storage density and improved endurance. By the early 2010s, SSDs became an increasingly viable option for mainstream consumers, first as upgrades for older systems, and then as standard equipment in new laptops and desktops. This gradual but relentless march of technology eventually pushed HDDs into a more niche role, primarily for archiving vast amounts of cold data, where cost per terabyte remains the sole priority. Today, the influence of solid-state drives extends far beyond simply making our personal computers faster. In the gaming world, SSDs are now a mandatory component. Consoles like the PlayStation 5 and Xbox Series X were designed from the ground up to leverage NVMe SSDs, virtually eliminating load times and enabling new possibilities for open-world game design that stream assets at incredibly high speeds. In professional content creation, from video editing to 3D rendering, the ability to rapidly access and process massive files directly impacts workflow efficiency and project completion times. Data centers, the backbone of the internet, have seen a dramatic transformation. SSDs accelerate database queries, improve the performance of virtual machines, and handle the intense I/O demands of cloud computing, making everything from online banking to streaming video services faster and more reliable. Even in the realm of artificial intelligence and machine learning, where vast datasets need to be moved and analyzed, SSDs provide the necessary bandwidth, directly contributing to faster training times for complex models. Their impact is truly ubiquitous, underpinning much of the digital infrastructure we rely on daily. With so many options available today, choosing the right SSD can feel overwhelming, and making a misstep can limit your system's potential. One of the most common mistakes is treating an SSD like an old HDD, particularly when it comes to defragmentation. HDDs benefit from defragmentation because it physically rearranges scattered data for faster access. For an SSD, defragmenting is entirely unnecessary, offers no performance benefit, and can actually reduce the lifespan of your drive by causing excessive, unneeded write cycles to the flash memory. Modern operating systems are designed to recognize SSDs and disable defragmentation automatically, but it's worth double-checking. Another crucial yet often overlooked feature is trim. Trim is a command that allows your operating system to tell the SSD which data blocks are no longer in use and can be wiped. Without trim, the SSD might perform slower over time as it struggles to find empty blocks, leading to what's known as write amplification. Ensuring trim is enabled is vital for long-term performance and endurance. Beyond these maintenance considerations, hardware choices are critical. You'll primarily encounter two interfaces, SATA and NVMe. SATA SSDs, typically in a 2.5-inch form factor, offer a significant upgrade over HDDs, but are limited by the SATA 3 interface to around 550 megabytes per second. For most users, this is still very fast. However, for cutting-edge performance, NVMe SSDs are the clear winner. NVMe drives connect directly to the motherboard via the PCIe interface, offering speeds many times faster than SATA, ranging from several thousand megabytes per second for PCIe 3.0 to over 10,000 megabytes per second for the latest PCIe 5.0 drives. They often come in the compact M.2 form factor. The choice depends on your motherboard's compatibility and your specific workload. For a gaming PC or a professional workstation handling large files, an NVMe drive is almost a necessity. For a general-purpose laptop or an older system upgrade, a SATA SSD can still provide a huge boost. Furthermore, understanding flash memory types is important. SLC is the fastest and most durable, but also the most expensive and lowest capacity, typically found in enterprise solutions. MLC and TLC offer a good balance of performance, capacity, and cost, with TLC being the most common choice today. QLC packs even more data into each cell, leading to higher capacities at lower costs, but generally with reduced endurance and sometimes slower write speeds, especially after the SLC cache is exhausted. For everyday use, a TLC or even a good QLC drive is perfectly adequate, but for intensive, frequent writes, a TLC drive would be preferable. Finally, consider whether an SSD has a DRAM cache. Drives with DRAM generally offer better sustained write performance and more consistent speed compared to DRAM-less drives, which use your system's RAM or a portion of the QLC NAND itself as a cache, potentially leading to performance drops under heavy load. Always match the SSD to your needs and budget rather than simply buying the cheapest or most expensive option. As remarkable as the journey of the SSD has been, its evolution is far from over. Researchers are constantly pushing the boundaries of flash memory density, aiming for even higher capacities and smaller footprints. New interfaces and protocols are being developed to further reduce latency and increase bandwidth, preparing for the demands of future computing tasks like real-time AI processing and increasingly immersive virtual realities. We might even see the line between RAM and storage continue to blur, with persistent memory technologies offering memory-like speed for massive datasets that traditionally reside on storage. The goal remains the same: to make the storage layer of our computers so fast and seamless that it effectively disappears, allowing us to interact with data at the speed of thought. From sluggish hard drives to the lightning-fast performance we now take for granted, SSDs truly revolutionized how we interact with technology. They didn't just make computers faster, they enabled entirely new applications, fueled innovation in countless industries, and ultimately shaped the digital world we inhabit. If you found this dive into solid-state technology enlightening, consider subscribing for more insights into the tech that powers our world. Stay curious. This is AI Unpacked.